Hello, welcome to another module in this massive open online course. So, we are looking at OFDM, that is orthogonal frequency division multiplexing, and basically how it can be modeled and how linear algebra specifically can be used to model and analyze an OFDM system. And of course, as I have already told you, OFDM is a dominant technology that is used in 4G, 5G wireless systems. Let us now look at another interesting technology which is again used in 4G and 5G wireless systems also, which is known as Sc Fdma, single carrier frequency division multiple access, and I will explain to you the difference between OFDM and Sc Fdma in a moment. But Sc Fdma is also yet another dominant waveform that is once again used in 4G and 5G wireless systems. So, let us talk about Sc Fdma, and of course, remember this is a course on linear algebra. So, eventually we want to look at how linear algebra can be used to model this system, to build a model for this system. So, Sc Fdma, once again this is a another dominant technology that is used in 4G and 5G cellular systems. So, this is used in 4G, this is also used in 4G and 5G systems, and SCSD Fdma stands for single carrier frequency division for multiple access, right. So, and the difference between OFDM and Sc Fdma is the following, whereas OFDM is used in the downlink, that is the base station to mobile. Sc Fdma, the difference is that this is used in the uplink. That is, if I look at a cellular system, and of course, I have the mobile, I have a mobile, and this is the downlink, which is essentially your downlink, we are saying is OFDM, that is the base station to mobile. But if you look at the uplink from the mobile to base station, this is basically the uplink, and the uplink is basically your Sc Fdma, and this is in 4G as well as to a great extent in 5G. The reason being, why do we need to use a different modulation technique or a different waveform in the uplink as compared to the downlink? The reason is because OFDM, which is used in the downlink, suffers from a unique problem. This is known as PAPR, that is peak to average power ratio. OFDM has a high peak to average power ratio because remember, in OFDM the IFFT is performed prior to transmission. So, in OFDM we have IFFT processing. OFDM, because of IFFT, this implies this is high PAPR, that is your peak to average power ratio. Therefore, because of high PAPR, so OFDM is not efficient for the uplink. So, it can be used in the downlink, that is the base station to mobile, but this is not efficient to the, for the uplink. And therefore, the question is what can now be used in uplink. So, uplink one cannot resort to multi-carrier transmission, that is one cannot use the IFFT. So, uplink is still single carrier, and that is essentially what is known as single carrier frequency division for multiple access. So, therefore, uplink, so basically multi-carrier not suitable for uplink, which implies single carrier. Which implies that single carrier transmission is preferred for the uplink, and but we would like to retain the frequency division multiple access that is there in OFDM plus FDMA. We would like to retain the FDMA structure, that is the frequency division for multiple access. We would still like to retain that aspect, but without the multi-carrier transmission. So, single carrier plus frequency division multiple access, how is that possible? And the procedure for that is as follows. So, Sc Fdma, what is the procedure, right? So, we begin by asking the question Sc Fdma, what is the procedure for Sc Fdma? So, Sc Fdma, what we do is we take the symbols, as I already told you, we do not do the IFFT, we directly transmit the symbols. So, in this case you have the time domain quantities x0, x1 up to xn minus 1 . These are the symbols, not IFFT samples. I think this is important to remember. In Sc Fdma, you are directly transmitting the symbols, that is the modulated information symbols, that is your BPSK or QPSK symbols, not the IFFT samples at the output of IFFT. In fact, there is no IFFT at the transmitter. So, these are the directly, so these are basically what you are transmitting, these are basically the modulated symbols, not the IFFT samples, but nevertheless we add the cyclic prefix. So, nevertheless we add the, so these are your symbols. So, this is essentially this is your cyclic prefix. So, remember this is making the whole symbol look cyclic, right. It makes it look as if it is a periodic signal. Therefore, what happens is the channel, the convolution between the channel and the symbols, that becomes a circular convolution, right. So, I can express this as a result of this. So, adding Cp, because of Cp, remember similar, this is similar to OFDM, because of Cp convolution channel and symbols becomes a circular convolution, and remember that is why you have the circulant matrix. Remember that circulant matrix that represents the circular convolution. Nevertheless, if you write this, you will have the output ym equals hm. Again you will have the same this thing ym equal to hm circularly convolved with xm plus wm. This is essentially your circular convolution. This is essentially your circular convolution, and therefore, now if you look at the outputs, if you write the, and these hm you might well recollect, these are your h0, h1 up to hn minus 1, these are the channel taps, right. So, these are your n channel taps and these represent the ISI channel. You remember we went through this discussion, as the bandwidth increases, symbol time decreases, symbol time decreases. Essentially what happens is the symbols are smeared out by the channel, and therefore, this results in intersymbol interference, so on and so forth. Such a channel can be represented as the using the multiple channel taps, and now essentially therefore, if you look at this output, therefore, now look at this. So, we do not perform the IFFT prior to transmission. So, now here the, of course, the thing you have to remember in Sc Fdma is in Sc Fdma no IFFT prior to transmission. Right. This is the major difference with respect to OFDM. There is no IFFT performed, that is prior to transmission. You are simply taking the symbols, block of n symbols, adding the cyclic prefix and transmitting it over the channel, which of course it is a intersymbol interference channel. And therefore, you will have the output will be, if you look at y0, y1, yn minus 1, this will be hc times x0, x1, xn minus 1 plus you will have the w0, w1, w n minus 1. So, this is, you can call this as your y bar, this is your x bar, and this is your w bar. And remember, your x bar, this is directly your symbol vector. So, you are transmitting the symbols, not the samples, right. And therefore, I can represent this as y bar equal to hc x bar plus w bar. This is your symbol vector, and this is your circulant matrix. Hopefully, all of you remember that the circulant matrix is basically one in which each successive column or each successive row is obtained by circularly shifting the previous row or column. In fact, the first column simply comprises of the channel taps h0, h1, hn minus 1. Each subsequent column is obtained by downshifting, circularly downshifting the previous column. Okay, so, this is your circulant matrix, and the interesting circulant matrix comprising of the channel in terms of the channel taps, not a problem, you can write it down, that is your h0, h1, hn minus 1, H n minus 1, H 0, H 1, so on, H n minus 2, H n minus 1, H 0, so on, and this is essentially what will be your, this is your n cross n circulant matrix. And if you look at the first column in this, this is nothing but basically your channel taps, that is your channel tap vector, and each column will be basically obtained by circularly downshifting the previous column. Okay. And therefore, now we have y bar equal to h c times x bar where h c is a circulant matrix. Now, recall I can write the eigenvalue decomposition of h c as f of the IFFT matrix, which are the eigenvectors, lambda diagonal matrix of eigenvalues, which is nothing but the FFT coefficients or DFT coefficients of the channel taps, times IFFT matrix inverse, which is nothing but the FFT. So, this is basically the eigenvalue decomposition. This is the eigenvalue decomposition, and this is the of course IFFT FFT matrix, and this is the diagonal matrix of eigenvalues. Diagonal matrix of eigenvalues, and these eigenvalues are nothing but your DFT coefficients. This is the zero DFT coefficients of the channel taps. These are the DFT coefficients of the channel taps, and therefore, now if you substitute this, what you will have is that you will have y bar equals, well, f IFFT lambda f FFT times x bar plus w bar. Now, apply again similar to OFDM. Now, this part is similar to OFDM. Apply FFT at receiver or perform FFT at receiver. This implies you will have f of FFT times y bar. This will be equal to f of FFT times f of IFFT times lambda f of FFT into x bar plus w bar. Now, f FFT into f IFFT, this is equal to identity. So, this will simply be lambda times f of FFT times x bar plus w bar, which is basically your noise vector. This is basically x bar is your symbol vector, this is your FFT matrix. this is basically your FFT matrix. Remember ijth entry equal to w raised to the power of I minus 1, w raised to the power of w raised to I minus 1 j minus 1, where w equal to e raised to j 2 pi or e raised to minus j 2 pi over n, and of course, lambda is the diagonal matrix of eigen values, which are nothing but the DFT coefficients of the channel taps. And essentially, and here we have used the property that we have used is basically that f of FFT times f of IFFT equals identity, because we are applying the FFT at the receiver. That is, applying the FFT at the receiver is nothing but you can think of it as processing with the FFT matrix, that is FFT, that is what we have seen before. That is, the FFT operation can be represented as multiplying with this FFT matrix, whose ijth entry is w raised to the power I minus 1 into j minus 1, where w is e raised to j 2 pi over n, n is the number of subcarriers. So, please understand each and every step and each and every quantity that is involved thoroughly. If you understand it, it is very simple to follow. Okay. Now, let us, what we do is we obtain this, let us call this as y bar. This is similar to what we obtain in OFD and capital Y bar. So, you have the capital Y bar equals lambda f FFT times x bar plus w bar. Now, we do the single tap equalization, that is, on each subcarrier divide by the channel coefficient. Overall, we perform lambda inverse, where lambda is a diagonal. So, this equalization, this is an interesting term. This essentially means flattening the channel response, right. So, that is essentially where you are equalizing the channel response, and that is why you are dividing by HK. The channel is HK, dividing by HK to flatten the response, that becomes your equalization. So, the equalization in this case is simple, that is your single tap equalizer. So, remember YK divided by HK, this is essentially your equalization, and basically this is your single tap. Since you are dividing by only one quantity, that is your HK, this is your single tap equalizer. This is your single tap equalizer. Okay. And therefore, what we are doing is we are performing lambda inverse overall. If you look at it, y bar, which becomes lambda inverse times f or lambda f FFT x bar plus this is your, we call this as the capital W bar. So, this is your f FFT times, so this is essentially your capital W bar. What is this capital W bar? This is FFT at the output of the noise at the output of the FFT. So, this is f FFT times the small W bar, right. So, this is your noise, output noise, output of what? Output of the FFT. That is your capital W. Okay. So, this is your W bar, which now gives you lambda inverse lambda is identity. So, that gives you your FFT, f FFT x bar plus lambda inverse W bar, that is because your lambda inverse lambda is identity, and remember lambda is a diagonal matrix, therefore it is easy to invert. Remember lambda, if you look at, if you recall the structure of lambda, this basically contains simply your DFT coefficients of the channel taps. Okay, so these are basically the DFT coefficients, or these are your FFT coefficients of the channel taps. Right, and we also saw what we mean by HK. HK equals summation n equal to 0 to capital N minus 1 h n e raised to minus j 2 pi n k over n. This is essentially the kth DFT coefficient. Or FFT kth DFT coefficient or FFT coefficient. Okay. And now what we perform after this single tap equalization, remember in OFDM the estimation process ends with single tap equalization, because there you are pre-processing using the IFFT matrix, but here that is not the case. We still have to recover the symbols x bar, right, the small x bar. Therefore, we now have to perform FIFFT, that is FIFFT times lambda inverse y bar, that is now perform IFFT. So, at receiver in Sc Fdma we are performing both FFT and IFFT. Contrast this with OFDM where you are performing IFFT at transmitter, FFT at receiver. In OFDM nothing at the transmitter, both IFFT and FFT, FFT followed by IFFT at the receiver. Alright. So, this will be FIFFT lambda inverse y bar, which is FIFFT times FFT x bar plus lambda inverse capital W bar, which if I call this as y tilde, right. Now, if I call this as y tilde, what you will see is this y tilde equal to FIFFT to FFFT's identity. So, that will be your x bar plus FIFFT times lambda inverse capital W bar. Let us call this as W tilde. So, essentially what you will have is, now after the IFFT you will have y tilde, which is basically your n cross 1 vector, equals x bar plus W tilde, where both of these are also naturally n cross 1 vectors. And therefore, what this essentially means is, now you have a very simple model y tilde 0 equals x of 0 plus W tilde 0, y tilde 1 equals x of 1 plus W tilde 1, y tilde n minus 1 equals x of n minus 1 plus W tilde n minus 1. Now, why go through all this frequency division multiplexing when you want to simply transmit using a single carrier? The advantage is you still have a decoupled system, and more importantly the equalization can be performed using the FFT and IFFT operations. This is not possible in a conventional single carrier system. So, remember one thing, although this is a single carrier system, but the processing becomes much easier because it is being done using the FFT and IFFT, which can be done in a very fast fashion. You know that from your knowledge of signal processing. FFT and IFFT are very fast, rapid, complexity is n log 2 to the base log n to the base 2. In comparison to that, if you have to do conventional equalization, which you have to invert n cross n matrices, that will be n cube, much higher complexity. So, the single carrier FDMA complexity, equalization complexity is still much lower because of FFT, IFFT processing, right. So, you will understand this aspect from this model. So, what is the difference here? You still get a decoupled model, right, you will still get a decoupled model, but processing is easier, processing in Sc Fdma is much easier in comparison to conventional single carrier systems. Processing in Sc Fdma is much easier in comparison or when compared to conventional because of IFFT, FFT operations. Right. So, it is a single carrier system, but the frequency division multiplexing aspect that is introduced by these IFFT, FFT operations that make the equalization, the overall equalization much more simpler in the Sc Fdma in comparison to conventional single. Now, comparison to OFDM, Sc Fdma complexity is relatively same, right, because in OFDM you are doing IFFT at transmitter, FFT at receiver. Sc Fdma you are doing both IFFT and FFT at the receiver. So, complexity is more or less same in comparison to OFDM. But hardware complexity, once again realize this, in Sc Fdma is much lower, because I already told you in OFDM you have the problem PAPR. Because of PAPR there are several other problems. Once there is power becomes very high, right, the peak or the peak in comparison to average, that is what we call as the dynamic range of that signal becomes very high. Designing hardware is very difficult, in particular because the bias point cannot be effectively designed and so on, and the non-linearity effects start to kick in. Sc Fdma, because it is single carrier system, PAPR is low, it means hardware complexity is much lower. So, Sc Fdma hardware complexity is much lower. Because low PAPR. Because of the low PAPR. So, hardware complexity is much lower, and as we have seen, the overall system model is basically after the IFFT you will have y tilde 0, y tilde 1, y tilde n minus 1, right. This is equal to your x of 0, x of 1, x of n minus 1, plus you will have your w tilde 0, w tilde 1 up to w tilde n minus 1. So, this is your y tilde, this is your x bar, this is the noise w tilde, and you know that this x bar contains the transmitted symbols. So, essentially what you are doing is you are transmitting the symbols, time domain symbols itself, and because of the IFFT FFT operations you are sort of performing the equalization in the frequency domain. So, look at this, at the receiver you are doing the FFT followed by the equalization followed by the IFFT. So, equalization is done in the frequency domain. This is also roughly known as frequency domain equalization, right. So, although it is not exactly the same thing, implies in Sc Fdma equalization is being done in the frequency domain. So, this is also often referred to as FDE. Also often referred to as FDE, frequency domain equalizer. So, essentially you are saying, what you are saying is it is much easier to do equalization in the frequency domain, especially after you are transmitting adding a cyclic prefix, because everything is circular. So, you can operate using the FFT and IFFT operations. So, the equalization is implemented in the frequency domain where you have single tap equalizer. Remember, that is the advantage. You have the diagonal matrix lambda multiplying by lambda inverse, that is a single tap equalizer, and therefore, you have frequency domain equalization, and then you are reconstructing the symbols back using the IFFT. Alright, so FFT equalization, IFFT get back the equalized symbol. Alright, so that essentially is the principle of Sc Fdma, which is once again used in 4G, used in 5G, again one of the most important technologies and waveforms that we have currently, and once again you can see how all of this can be neatly modeled in a very compact, succinct fashion using linear algebra, matrices and so on, and you do not need a lot of how do you put it, complicated mathematical manipulations to describe this. Once you have the framework in terms of the FFT and IFFT matrices and the eigenvalue decomposition of the circulant matrix, you can see it falls, it comes out very neatly simply using the eigenvalue decomposition of the circulant matrix and followed by these FFT, IFFT operations, which are once again all represented using matrices. So, that is the advantage of linear algebra matrix analysis. It gives you a powerful tool to represent these operations in a succinct fashion and gain valuable insights. All right. So, let us stop this discussion here. We will continue in the subsequent modules. Thank you very much.